My name is David Morilla-Cabello, and I will present our working collaboration between the University of Zaragoza and the University of Bonn. How to interpret the information provided by neural networks for active perception? This was the initial question that brought us to this work. Let's say that we have the following task. What is the type of plant in our living room? One common pipeline is to use a camera to take images and a neural network that will interpret certain features from the environment rendered on the image to give a label. Now, if we only move slightly and take another image, we will probably get the same label. And now my question is, should we be more confident about the plant type? If you see both images, they are quite similar. Another way of putting it is that they are correlated measurements. In fact, the predictions from the neural network are conditioned on certain variables such as color and appearance, which are very similar in both images. So let's see what we can do about it. In addition to the problem before, there are other factors such as light conditions, partial occlusions, that also affect the prediction of the neural network. Let's move on to this scenario where a robot is trying to recognize the object on top of the table and is reasoning about where to move next to get a better observation. What we propose is to account for this additional information that we term perceptual factors. However, as you can imagine, these are impossible to model. Our solution proposes to approximate it by a perceptual influence map that you can see on the bottom left. This map is built by combining a set of different functions that express the correlation with viewpoints that yield similar appearance and external factors such as objects and backlighting. The parameters of these functions are previous poses, the position of other objects in the scene, and lights. And we currently use analytical handcrafted function as a simplification. The question now is, how do we use this map? In short, we use its value at a specific point to represent the expected information value. This is introduced in traditional fusion frameworks by weighting the uncertainty associated to the measurement. For example, in the Kalman filter, we can include it as an scaling factor of the covariance matrix. Or in Bayesian fusion, as in the semantic case, we can include it as a weighting term that will avoid overconfidence due to re-observations and the effect of outliers caused by the perceptual factors. And finally, if we get an overview of the typical planning pipeline, we include the perceptual map in the information fusion step, and during the information gain estimation of the planner, as this one normally requires a simulation of the information fusion. Then our robot will know where to move to re-observe the object correctly. To evaluate this framework, we perform simulated experiments in the task of active target localization and semantic classification. Something important is that we need a simulator that incorporates the perceptual effects. We also deploy the planning pipeline in a real robot. As I said, for the simulator, we need to model how perceptual factors affect the observations. We do this by studying how a real object detector behaves in terms of the noise applied to the observations and the confidence output of the detected classes. You can check the details in the paper. About the tasks, in the case of active target localization, we approximately know the pose of the target with some error and large uncertainty. In the classification case, we know the position of the target and have to discover its class. For both cases, we use an entropy reduction-based greedy planner and compare the results when considering perceptual factors. We can see from the results that by considering perceptual factors, their effect can be avoided and the outliers filtered. This results in an improvement of the quality in both tasks. Better consistency in the filter estimation, this is a better calibrated uncertainty with respect to the error, and better average confidence of the true class in the active classification. We also deployed this framework in a real robot and scenario. In this case, the task is to identify a hotel in a known position. As you can see from the footage, the naive planner has no information about the environment and it is affected by the perceptual factors. Additionally, we had to manually prevent the choice of staying in the same viewpoint, and it has no notion of viewpoint correlation. In our case, our planner automatically avoids perceptual affected areas and observes from distinct viewpoints. This results in a better mission performance by incorporating perceptual factors into planning. As a conclusion, we propose a new framework considering environmental correlations in active perception. This results in better and more robust information value estimation and improved planning for active perception. As future steps, a further analysis of the factors modeling is key. We think that learning approaches will be relevant in this direction. Also, better inference setups such as factor graphs are really suited to this framework, and sharing the perceptual information about the environment with other agents is also interesting. Thank you for your attention and don't hesitate to reach out if you have any questions.